Normality test using SPSS, how to check whether data are normally distributed. As you know, in many statistical analyses, there are dependent variables and independent variables. A dependent variable is a variable that may depend on other factors. For example, exam scores as a variable may change depending on the student's gender. An independent variable, on the other hand, is a variable that doesn't change. For example, gender doesn't change depending on exam scores. Many parametric statistical methods require that the dependent variable is approximately normally distributed for each category of the independent variable. The normal curve is the familiar, classic bell-shaped curve. In our example, exam scores need to be approximately normally distributed for both males and females. Let's use SPSS to verify this. We must investigate the following numerical and visual outputs. The skewness and kurtosis Z values should be somewhere in the span of minus 1.96 to plus 1.96. The Shapiro-Wilk p-value should be above 0.05. The histograms, normal QQ plots and box plots should visually indicate that our data are approximately normally distributed. Remember that your data doesn't have to be perfectly normally distributed. The main thing here is that they are approximately normally distributed and that you check each category of the independent variable. In our example, we must check both male and female data. Now I will show you how to do it with the help of SPSS. Afterwards, I will provide references and show examples of how you can write out your results in your paper or article manuscript. In the SPSS menu, click on Analyze and select Descriptive Statistics, then Explore. In our example, exam scores is the dependent variable because, as I said, we assume that they may change depending on gender, and gender is our independent variable. Next, click on Plots and select histogram. You don't need stem and leaf. Select normality plots with tests and continue. Click OK to execute and generate the output. First, focus on skewness and kurtosis. The measures are in the left column and their standard errors are in the right column. The skewness and kurtosis measures should be as close to zero as possible in SPSS. In reality, however, data are often skewed and kurtotic, as you know. A small departure from zero is therefore no problem, as long as the measures aren't too large compared to their standard errors. As a consequence, you must divide the measure by its standard error, and you need to do this by hand using a calculator. This will give you the Z value, which, as I said, should be somewhere between minus 1.96 and plus 1.96. Let us start with the males in our example. To calculate the skewness Z value, divide the skewness measure by its standard error. Here it is 1.02. This value, 1.02, is neither below minus 1.96 nor above plus 1.96, which is exactly what we want. Next, calculate the kurtosis Z value for the males. In this example, it is 0.81, which is also within plus minus 1.96. Next, calculate the skewness and kurtosis Z values for the female data. It is minus 0.03 and minus 1.16. All four Z values in our example are within plus minus 1.96. Hence, we end this part about skewness and kurtosis by concluding that the exam score data are a little skewed and kurtotic for both males and females, but they don't differ significantly from normality. Next, let us focus on the Shapiro-Wilk test statistic. The null hypothesis for this test of normality is that the data are normally distributed. The null hypothesis is rejected if the p-value is below 0.05. In SPSS output, the p-value is labeled SIG. In our example, the p-value for males, 0.456, and females, 0.493, are both above 0.05. So we keep the null hypothesis. The Shapiro-Wilk test thus indicates that our example data are approximately normally distributed. Next, let us look at the graphical figures for both males and female data. Start by inspecting the histograms visually. They should have the approximate shape of a normal curve, and I think they have in our example. So everything is okay here. Then look at the normal QQ plot. The dots should be along the line. This indicates that the data are approximately normally distributed. In our example, I think they are approximately distributed along the line, so it's okay. Skip the detrended QQ plots, you don't need them. Look at the box plots, they should be approximately symmetrical. Although they are not perfectly symmetrical in our example, I think they are good enough. Finally, before I show you how to write out your results, let me provide the sources. These are the books and articles that are the basis for this tutorial. This is how I would write out the results. I would put it under the subheading Sample Characteristics. And I would phrase it something like this. Feel free to pause the tutorial now to read my example text more in detail. In case you are wondering, you don't need to report the skewness and kurtosis Z values. It's enough to report the measures and their standard errors. SE is the abbreviation for standard error. In this tutorial, I've showed you how to check if a dependent variable is approximately normally distributed for each category of an independent variable. I did this because I assumed that you eventually will want to use certain parametric statistical methods to explore and investigate your data, such as, for example, t-tests. If it turns out that your dependent variable is not approximately normally distributed for each category of the independent variable, it is still no problem. In such case, you will have to use non-parametric methods because they make no assumptions about the distributions. Thank you very much for watching, and let me end by wishing you success with your research and your paper or article manuscript.